Guys, in this video, we will discuss about that how to solve the linear differential equation which is of the form dy dx plus p of xy is equal to qx. How to solve. So basically, if we compare it, that it is a non-exact equation. It is a non-exact equation, and we know that we are able to solve an exact differential equation. But how can we solve a non-exact differential equation? To solve the linear differential equation means its order is 1 and also degree is 1. And here we will going to discuss about how to solve a non-exact differential equation whose order 1 and degree is also 1. How can we solve? So here let's say that if this differential equation, this is a order 1 and degree 1 equation, and this is non-exact because if we compare it with mdx plus ndy is equal to 0, where we can say that this symmetrical form of the differential equation is exact if del m del y is equal to del n del x. And now you can, by watching, you can say that this one is always non-exact. So how can we make it exact and how can we make the solution? So here I will use a new term, the integrating factor. The integrating factor means this is a integrating factor is a quantity which make a non-exact equation to exact. So for the linear differential equation, the integrating factor is of the form that e to the power integration p of x dx. And when we find the integrating factor of a linear differential equation, then how can we solve? After integrating, find the integrating factor, we have to multiply by the integrating factor of this equation. Then what we get? That is e to the power integration p of x dx of dy dx plus p of x into y is equal to e to the power integration p of x dx into q of x, and then in the left hand side we will get that ddx of y into integrating factor e to the power integration p of x dx is equal to e to the power integration p of x dx into q of x, and then we will get d of y into integrating factor here is equal to integration of e to the power integration p of x dx into q of x dx. And we have to solve this one, and from here we will get the answer that y into integrating factor is equal to integration of e to integrating factor e to the power integration p of x dx into q of x dx plus c. So this is the form that after multiplying by the integrating factor, here you have to know that after multiplying by the integrating factor, the non-exact equation become exact. After multiplying by the integrating factor, the non-exact equation become exact. So now let us try to solve some problems which is a linear differential equation, and let us discuss about all those problems. So see here that this is a dy linear differential equation dy dx minus 2 by x plus 1y is equal to x plus 1. If we compare it with the equation dy dx plus p of xy is equal to q of x, see here that p of x is equal to minus 2 by x plus 1 and q of x is equal to x plus 1. So here this is the integrating factor, that is I is e to the power minus 2 into integration dx by x plus 1. So we will get e to the power minus 2 log of x plus 1, and from here we will get this is 1 by x plus 1 whole square. So now the question is that how now we have to multiply this integrating factor of the both side of the equation. So what we get after multiplying by the integrating factor? So here we get after multiplying by integrating factor, that is if, we will get 1 by x plus 1 whole square dy dx minus 2 by x plus 1 whole cube y is equal to x plus 1 by x plus 1 whole square. And after multiplying by the integrating factor, in the previous slide I say that we will get that here d of the dependent variable y into integrating factor, and here integrating factor is 1 by x plus 1 whole square. So we get d of y by x plus 1 whole square is equal to ddx of y by x plus 1 whole square is equal to 1 by x plus 1. Or from here we can write that d of y by x plus 1 whole square is equal to dx by x plus 1. And now if we, after integrating, we get y by x plus 1 whole square is equal to log of x plus 1 plus c, where c is the arbitrary constant. C is the arbitrary constant. So by this we can solve a linear differential equation. Let us solve another two problem. Here that is this problem, that dy dx plus 2y tan x is equal to sin x. Here the question is of the form dy dx plus 2y tan x is equal to sin x. And if we compare it with dy dx plus p of xy is equal to q of x, here p of x is 2 tan x, q of x is sin x. So the integrating factor here, that is e to the power integration 2 tan x dx. So from here we will get e to the power 2 log sec x, and so from here it will be sec square x. And now if we multiply by the integrating factor, so what we get, sec square x dy dx plus 2y tan x sec square x is equal to sin x into sec square x. And after multiplying by the integrating factor, in the left hand side we get d of y into integrating factor is equal to ddx of y sec square x is equal to, we get sin x into sec square x. That means from here we will get, this is sec x tan x, and so if we now multiply, so now we get d of y sec square x is equal to sec x tan x dx. And so from here, if we now integrating, what we get, now if we integrating, after integrating, what we get, that is y sec square x is equal to sec x plus c, or y is equal to, from here we get sec x plus c into cos square x, where c is the arbitrary constant. C is the arbitrary constant. So now I hope you understand how can you solve this one. And now I am going to solve the last problem for here. That is, here the question is dy dx minus 2y by x is equal to x square e to the power x. That is, here if we compare it with the equation similarly, dy dx minus plus p of xy is equal to q of x. Here p of x is equal to minus 2x and q of x is equal to x square e to the power x. So the integrating factor here is of the form e to the power integration minus 2x dx. So it will be e to the power minus 2 log x. So from here we will get, this is 1 by x square. So now if we multiply by the integrating factor, multiplying by integrating factor, what we get? That is 1 by x square dy dx minus 2y by x cube is equal to e to the power x. And in the right hand side, we will get d of ddx of y by x square is equal to e to the power x. And now if we both side integrating, or d of y by x square is equal to, if we both side integrating now, we will get e to the power x dx, and now we will get y by x square is equal to e to the power x plus c, where c is the arbitrary constant. C is the arbitrary constant, and so what we get, y is equal to e to the power x plus c into x. And now I am going to show you another one type of problem here. So I hope you understand how can you find the solution of a linear differential equation. And here now I'm going to show you another one type of problem here. Let's say this is the question 1 plus y squared dx minus tan inverse y of minus xg. So here if you compare it with m dx plus n dy is equal to 0, where m is equal to 1 plus y square and n is equal to x minus tan inverse y. And from here you can say easily that del m del y not equal to del n del x. So now how can we solve? So let's see that how can we solve. So from here can we write that or 1 plus y square dx dy plus x is equal to tan inverse y, we can write. Or from here can we write that or dx dy plus x by 1 plus y square is equal to tan inverse y plus 1 by y square. And now if we compare it with the one type of linear differential equation, dx dy plus p of y of x into x is equal to q of y. See that here p of y is 1 by 1 plus y square and q of y is tan inverse y by 1 plus y square. So now this is one type of another linear differential equation. So here the integrating factor is of the form e to the power integration p of y dy. And here what is p of y? That is here p of y is e to the power integration 1 by 1 plus y square dy. So here we get e to the power tan inverse y. So now after multiplying by the integrating factor, what we get here? That is we will get here, after multiplying by the integrating factor, that e to the power tan inverse y dx dy plus x e to the power tan inverse y by 1 plus y square is equal to e to the power tan inverse y into tan inverse y by 1 plus y square. So in the left hand side we will get our d of x e to the power tan inverse y is equal to, or d dx of e tan inverse y is equal to e to the power tan inverse y into tan inverse y by 1 plus y. Or from here we will get d of x e to the power tan inverse y is equal to, now if we integrate we will get e to the power tan inverse y into tan inverse y by 1 plus y square. So now how can we solve this one? So now I am going to the next new slide. That is here we will get that integration g of x e to the power tan inverse y is equal to integration e to the power tan inverse y into tan inverse y by 1 plus y square. Here if we solve it, that tan inverse y is equal to z, so 1 by 1 plus y square dy is equal to dz. So we will get here it is in integration z e to the power z dz. And now if we solve it by using the Bywords method, so here z is the first function and e to the power z is the second function. So we will get z into integration e to the power z dz minus integration d dz of z integration e to the power z dz whole dz. So from here we will get z e to the power z minus integration e to the power z dz. So it will be z e to the power z minus e to the power z plus c, or in the left hand side we will get x e to the power tan inverse y. So from here we will get z minus 1 e to the power z plus c. So if we put here the value of z, we will get tan inverse y minus 1 into e to the power tan inverse y plus c, or we will get x is equal to tan inverse y minus 1 plus c e to the power minus tan inverse y, where c is the arbitrary constant. So I hope you understand that how to solve this linear differential equation of first order and first degree by using the integrating factor. So thank you for watching the